Thank you very much for the nice introduction. Thank you very much for inviting me. It's a great pleasure to be part of this very fascinating workshop. So, my name is Tobias Preis. I'm an associate professor of behavioral science and finance, and I'm co-directing the data science lab at Warwick Business School together with my colleague Susie Mote. As heard before, I perhaps have not the most common background to work in a business school, being a physicist by training. So the reason why I'm enjoying to work at Warwick Business School today is actually that something quite fundamental has changed over the last few years. And this is the way how we as society interact with large technological systems. So from buying bread in the supermarket to taking a ride on the tube or your favorite transportation system in your home city, to actually just calling a friend for a chat. All of this nowadays generates data with our little small devices and creates a record of what people are interested in, what they want to share with others, or just where they are. So these new forms of data, these data sets are global. They can actually be very cheap. So in fact, some of them are available for free, shared by the companies collecting them. And they are very fast. So they're almost immediately after their generation accessible. To give you a flavor of the kind of data set I'm talking about, I would like to show you this slide, which is just constructed by taking 35 million photos which were uploaded by users of the photo sharing site Flickr during the year 2014. It shows the global distribution of popularity, to some extent reflecting how many people are in certain areas, but also the popularity where people like to take photos. In the right bottom corner, you, for example, see a zoomed-in version of Europe with Paris. And these data sets allow us to actually feed into three major areas in which we want to make progress in order to provide commercial and governmental stakeholders with information on possible interventions. So these three areas are, number one, these data sets might allow us to capture, to measure a little bit quicker what is going on in the world right now, because we might not know this. I will later on present an example. Secondly, if we know better what is going on in the world right now, then this information might help us to predict the likely future behavior of a group of people, not necessarily individuals. And number three, we can measure aspects of human life which wasn't accessible before. So over the next few minutes, I would like to showcase 5 examples fitting into these 3 categories. And the first example is actually based on our fascination of the global breadth of Google data, which actually provides us with information at a global scale, what people are interested in, which wasn't actually possible to study before. So in this first example, we were interested in the question to which extent people, citizens around the globe, are engaged, interacting with future and past. We were retrieving data on how many people search for keywords in order to measure this aspect. One problematic technicality of this problem is that search volume is obviously bound to natural languages. Our world is structured, clustered into natural language areas of different types. And this makes it difficult to compare search volume across the globe. So what we did in terms of coming up with an estimator of our attention towards future and past is to identify keywords which are commonly shared across languages. So in fact, what we downloaded via the service trends.google.com is how many people have searched over time in a particular year for Arabic numerals, special Arabic numerals. We use the year numbers, which are shared across languages around the globe. So in this example here, when we came up with this, what we call future orientation index, we used how many people have searched for the term 2011 during the year 2010, compared to how many people still searched for the past year, 2009. By constructing this index, which is in fact just a ratio in 45 different countries around the globe for which Google provides search volume and which have 5 million internet users each in order to ensure that we have a reasonable data quality underlying, we found that when we plot this index against one key economic variable, in fact GDP per capita, that there's a very striking relationship. We find a correlation of 0.8 roughly between this future orientation index, where 1 means the same number of searches carried out for the next year compared to the past year, and the economic success of these countries in question measured by GDP per capita. So we came up with 2 hypotheses actually quantifying or actually explain, which might explain this relationship which we see. And this, number 1, is that there is indeed a relationship between how we engage with future and past and how well our economies are doing. And a striking second hypothesis that actually this has something to do with the bias in internet infrastructure we see around the globe. Obviously, there's a bias towards the Western and more developed world, which might to some extent also affect the way how we use the internet, because there's more information available about the future rather than the past. So that's an example of a new measure which might help us to understand how search volume can actually be constructed and used around the globe. And in another second leading study, we wanted to ask the question whether we can actually use what people are searching for in order to find out what in another complex system, as we have discussed over the last couple of days a lot, the financial markets, we can get any insights into the relationship there. So what we have done is we just constructed a very hypothetical trading strategy historically, which used as an input how many people are searching for a specific keyword. And we have, for this data set, a weekly granularity. So we use the information how many people search for a specific topic in the current week. And we compared this with volume in the previous weeks in order to get an idea whether more or less people are interested in a particular topic. If, like in this case, less people were interested in it, we actually triggered a buy transaction, a hypothetical buy transaction in the market. We bought the Dow Jones Industrial Average in this concrete example and kept this long position for exactly 1 week. If the opposite case was registered, like more people were searching for a particular topic, then we opened a short position, we profited over the coming week if the market index went down. So let me show you just very briefly what would have happened if we would have used the input, how many people have searched for the term culture over time in the US, and we have used this input on a weekly basis to make investment decisions. So in blue, you find the cumulative return, the cumulative profit of this strategy, which results in 5% more over this time period until February 2011 when we conducted this study. Compared to 16% if you would have just invested in the underlying index, the Dow Jones Industrial Average. And both of these figures are between this range of dashed lines there, which indicate the plus minus 1 standard deviation of random investment over this time period. So culture was one of the terms we looked at, and we wanted to understand, are there any driving factors within this, the space of all possible search terms? So we looked at a sample of 98 different keywords, some of them more financially related than others. And another second example, which in fact was the best performing keyword during this time period, was the term debt. So how many people in the US have searched for the term debt? And this results using exactly the same mechanism and strategy in 326%, outperforming random strategies, leading to something like +3 standard deviations over what you would have expected. So we were wondering if when we looked at the entire range of keywords, which was constructed in a way which combined financially related topics, as I said before, and non-financially related topics like culture, whether we could actually spot any pattern. And in fact, it tended to be the case that more financially related keywords resulted in a higher return using this very simple strategy over this time period. So in brief, we wanted to quantify, we wanted to find evidence, is the statistical evidence that in fact financially related keywords are more successful, and so we had to come up with a measure quantifying financial relevance. In brief, we measured this by counting the occurrences of these individual keywords in the Financial Times as a financial outlet, and compared this or normalized this by the fact how often this word is used in general literature, just by counting how often this word is used or coming back in terms of Google hits. We find that this financial significance, financial relatedness, is actually significantly correlated with the outcome, the returns within our study. So I could carry on in a longer presentation about the additional evidence we find that there seems to be a link, at least historically, between what people are searching for online and what information they access and what is going on in the markets, at least in this very simplified historical framework. For example, we find evidence from Wikipedia, so how often people access information on Wikipedia, which is made publicly available. Here you see that if we take the example of how often individual pages on Wikipedia for the Dow Jones components are visited, and we use exactly the same framework, we find confirming evidence, as well as when we replicate our idea of financial relevance, when we use the input of how many Wikipedia related finance pages are viewed over time, and vice versa, when we feed in something which we don't expect to be related to markets, like actors and filmmakers, then we find, luckily, that there is no relationship between how often these individual pages are viewed and the behavior in the markets. So very briefly, I just want to touch on this briefly because I want to show you also other examples. So when we actually turn this question around, when we don't come in with an initial hypothesis that actually financially related content might be a driving force, when we actually start brute force by taking semantic relationships between documents into account and use algorithms from computational linguistics, in fact, latent Dirichlet allocation, then we can actually find out which different classes of topics are related to what is going on in the markets afterwards. So what is actually triggering changes, not saying that there are any causal relationships, but at least the coincidence of actually changes in interest levels for certain topics and what is going on in the markets. So this is something which came from the other side and used all possible pages on Wikipedia, grouped this into semantic topics using this algorithm, and by ensuring that we actually correct for multiple comparison to not cherry picking the results, we find confirming evidence that financially related content in this form here classified as category business because we used objective labels by crowdsourcing the labelings in order to not influence the results. And a second topic, which is politics relating to subsequent moves in the markets. So this is one example where we can at least find some initial evidence that what people are searching for and which content they are accessing online, that this might actually reveal some clues about markets. Historically, we are not claiming that this is something which will continue over time. So a third example where these new forms of data might be able to give us a clue. This is a very old problem, counting crowds, to come up with estimates how many people are, for example, protesting in a city. So the common methods include that you actually take visual footage. You basically take an image, you grid this image into certain areas, you count the number of people heads you can see, and this is one of the methods which requires human resources, obviously, but also requires time to come up with these estimates. Very luckily, we had not only a very brilliant PhD student, but also access to a very unique data set in the city of Milan. We had the information on the interactions with the mobile phone network on a 10 minutes basis, every 10 minutes an update with a spatial grid size of 235 meters squared. So a very detailed data set, and you look at the center of the city of Milan in this case, and we wanted to actually calibrate what we find from or what we can access from the mobile phone network with the number of people being in a restricted area. So we had to come up with some measurements about the real world where we know for sure that a certain number of people have been there in the past. And obviously, this can be, for example, a football stadium. What we see here is actually the activity, the aggregated activity of the 9 grid cells which are centered around the stadium San Siro in Milan, which is the major football stadium, on 22nd of December 2013, when a major derby game took place between Inter and AC Milan. And you can see over time on that day that the measured activity via the internet connections opened, maintained, and closed during these time periods actually started to peak immediately before the game started. So these 2 vertical bars indicate the 2 halves of the actual game time. And we were wondering whether we can use this information in order to match very closely, to calibrate our mobile phone activity to the number of people actually being there, because we know how many tickets have been sold, we know how many people went through the barriers of the stadium. And when Federico Botta, our fantastic PhD student on this project, plotted these data sets for the first time, we saw during these 10 weeks period in these 10 games, a very distinct pattern that these spikes actually matched very precisely the activity we have seen not only in the calls and SMS activity, but also in the internet activity and another data set we had, the Twitter activity, which is crucial because Twitter activity could have been used without special access to a mobile or via a mobile phone carrier. So in brief, we find that there is a very close relationship, and in fact, the internet activity seems to be the best match between the number of people being in this restricted area and the number of connections measured by this mobile phone data set, where in this case we find an adjusted R-square value of 0.93, while other data sets still match this very closely. But obviously, when we think about this, it makes sense. So calls and SMS activity require our active attention to interact with our phones as well as actually releasing via the Twitter network information. However, internet activity is something which our phones in the background actually generate by asking servers whether a new email has arrived or other connections which are maintained in order to fill our apps with information. So this was another example where we actually were able to calibrate, to use data generated online or via the mobile phone network to a real-world problem in question, which obviously is of interest to a number of stakeholders, including obviously the police. I mentioned that Twitter data was a special case because this is a kind of data set which is to some extent publicly available, or at least the full data set commercially available. And so in another area where we wanted to more quickly measure what is going on in the real world, we turned back to a data set I have shown you at the very beginning. And this is the number of photos taken around the globe. And we looked at a data set which is collected by the Office for National Statistics in the UK, and we were looking at the International Passenger Survey. So in brief, this International Passenger Survey requires people being at the airport, interviewing arriving passengers where they have been over the past 12 months or so, and then aggregating this information over time, which is obviously human resource intensive, and requires afterwards to actually, the after processing steps, the post-processing steps require that it takes a certain amount of time until you can access this information. So this reporting gap was something we wanted to look into. And what we did is we used 140 million Flickr photos shared around the globe between 2008 and 2013 in order to reconstruct individual trajectories of users of Flickrs, how they actually have taken photos around the globe, basically reconstructing their travel patterns over time. And like in this survey, we used the information when they crossed basically a boundary. We used where they have taken most of their photos in the 12 months preceding this photo, taken, for example, for the first time in the UK. By using this, we actually can show in the 28 countries which are part of this international passenger survey that we have a very strong relationship between the detected number of Flickr users visiting the UK and the official estimates of visitors coming to the UK. As an additional note, we actually find that when we look at the number of people surveyed and the number of trajectories we reconstruct, that basically both of them are at the same order. It's around 15,000. And this indicates that obviously also in the other data set, the officially released data set, there's a certain kind of noise. And so it's in particular interesting that we actually are able to match this. However, we need to mention that there are also certain limitations. So for example, we can capture the level very well, but we are not actually capturing with this simple technique the year-to-year changes, which is a limitation. So this brings me to my last final example I wanted to share with you today. And this is another example which on the one hand side is subject to a reporting lag, reporting gap, and is an example which became famous in the area of computational social science, and in addition highlights a lot of problems in this area of study. And this relates to the flu and the service which later on was called then Google Flu Trends. So you might know that in 2008, 2009, Google engineers teamed up with the Centers for Disease Control in Atlanta in the US. So these centers are tasked with the effort of coming up with reliable estimates of how many people have the flu in the US. And this is done by actually interviewing and retrieving information of a network of doctors all over the US, asking the question how many influenza-like illness symptoms patients they have seen over the last week or so. In brief, this information, when the CDC has the final number, is 2 weeks old. So this is actually the time it needs in order to aggregate this information. And so whenever someone has to make a decision, and maybe crucial decision, intervention to close down an airport, this information is 2 weeks old. So in 2008, 2009, when they started to look into the possibility of using Google searches, they correlated this time series of the weekly number of influenza cases against all possible search terms in the database which Google had. They found out that the most correlated ones, in fact the top 30, indeed were related to the flu. There were, amongst them, there were a lot of flu symptoms people were searching for. So this was quite fascinating. It was a paper published in Nature. It was actually afterwards led to the construction of a service, Google Flu Trends, where this could be monitored over time and was rolled out to a number of countries around the world. Until something happened. Actually, people were quite concerned because at some point this service didn't work anymore so well. So Google got it wrong at some point. You can see that this red curve vastly overestimates the number of influenza cases in the real world in 2012, 2013, during that winter. And there are a number of reasons which are quoted that this actually happened. And amongst these reasons are that actually a new stem of the flu H1N1 occurred, and there was a lot of news reports around this story, and obviously people started to search for flu symptoms without being ill. In addition, a lot of other reasons have contributed possibly to this phenomena, because also if you think how the data is collected and aggregated over time, I'm talking about the search volume data, this is something which changes. So search algorithms, the Google search algorithm is changing. The way how this information is presented to us changes over time. The front end, which provides additional information, if you type in topic-related search terms, in particular flu symptoms in the US, there are special notices. So a lot of things and factors are changing over time. And so the question was, is this actually the end? So this got actually picked up by colleagues of ours, Alexandra Vespignani, David Lazar, and others. And basically, they identified these reasons why this actually is not longer working over time. So at the same time, we started to look into the possibility of fixing this to some extent. So what Google has done is to just rely on the correlations, on the most correlated search terms in order to come up with these estimates. What they didn't use is actually information which was also available at every given point in time. And this is the delayed information of how many people had the flu 2 weeks ago. So that's the first point. So that's something we could actually include in our model in addition. So this would be basically a so-called, basically baseline model, because this is the information which is officially available. And then the question is, how much in addition can we add by using data from the search domain, what people are searching for in terms of symptoms. So there's one catch. So we have seen that this behavior is changing over time. There are news reports on maybe a new stem of the flu and 1H1 or others. And so also the relationship, the proportion of people searching for symptoms and the number of cases in the real world is changing over time and is fluctuating. So at the same time, we have seen that this overestimation during this winter 2012-2013 started already earlier. So the winter before, also the red curve was actually at the really high end of the estimation. And so we actually wondered whether, in addition to using the information about the 2 weeks delayed data point, in addition, with actually allowing for human behavior to change over time might be actually the key. And what we did, we came up with a method which used a running window, a sliding window, in which we retrained our model in every week, allowing for changes in the proportion of people searching for these flu symptoms and the real-world numbers. So we basically recalibrated this example, and if you do this, you find that in an out-of-sample setting, you are able to improve your estimates against this baseline model by 16 to 53%, depending on which size of window you are used in order to retrain this relationship. So with this example, I would like to close. I hope I have demonstrated some initial evidence that these data, which are globally generated, which are fast, almost immediately accessible after their generation, and data which can be very cheap, can give us additional insights, complementary insights into processes in the real world, which might help us to measure a little bit quicker what is going on, and in some cases even might provide us some clues what might go on in the near future. Thank you very much.